How does LangChain's pre-built middleware pipeline work internally? And how would you inject a custom middleware to mutate inputs before they reach LLM? Generally speaking, middlewares are used to intercept the request and modify it and sends it to the next execution flow. For example, if I have a step A and step B in my execution flow, if I have a request R, what intercepts does is it intercepts the request and it modifies it. This is the modified request and sends the modified request to B. This is middlewares generally. In LangChain, what we can do with these middlewares is we can remove PI data from input and output. Here we have custom logic to scrub PII. We can run this custom logic using runnable lambda in LangChain. Here we are removing the personal identifiable information such as name from the input, and we are passing it to the prompt, and then we are passing it to the LLM using LangChain Expression Language, and we are getting the response. Here we are removing the name from the input. How would you implement hard guardrails in a LangChain agent to block unsafe or off-topic responses before they reach the end user? We can implement guardrails in LangChain with the help of middlewares. With these middlewares, we can intercept requests and responses and process the guardrails. These are the blocked topics: hack, exploit, bomb. If user enters any of these words, we have to block the user input from reaching LLM. In the output guardrail, if from the LLM, if we have a word dangerous, we have to block the response, and return response is blocked by output policy. Here we are implementing this flow by using LangChain's expression language. First we have an input guardrail, then we have a prompt, then we are passing it to LLM. Whatever the response we are getting it from the LLM, then we are passing it to the output guardrail. If user entered what is Python, then we are getting the output without any issues. But if user entered how to hack a system, then we are raising a value error that blocked unsafe user input detected. We are printing the same here. What is context engineering in LangChain agents, and how do you dynamically construct the agent context window to maximize reasoning quality? Context window is nothing but the agent session memory. Whatever the text present in the agent session memory is called as context. It includes prompts, generated output, retrieved information, everything. We can maximize the reasoning quality by continuously reducing the context window using the conversation summary buffer memory. What it does is, when context window reaches the limit, it summarizes the entire context to smaller size. Here we are configuring the conversation summary buffer memory. The max token limit is 200. Whenever the context window reaches 200 limit, what it does is it summarizes the entire context and reduces the context size, so it will be below 200. Explain the LangChain runtime execution model. How does invoke differ from stream and batch? When does each mode break under the production load? Invoke is synchronous. It invokes the LLM and gets the response in real time. Streams the tokens in real time. It is also synchronous. Coming to batch, it processes multiple inputs at a time, but it has a risk of API throttling under the load. All these three are not suitable for production because they are not asynchronous. In the production, it is better to have asynchronous APIs. For this, we have asynchronous stream and asynchronous batch. So if we use these things, it will be better in the production. We have LLM chain configured here. Here we are invoking the request and getting the response synchronously. Here we are invoking with the stream and we are getting the stream tokens. Here we are printing each chunk at a time. In batch, we are getting the response for multiple requests at a time. All these three are synchronous. For production loads, it is better if we use asynchronous stream. Here, if we are not getting the response in real time, the API will wait till we get the response and proceeds. How do you implement human in the loop approval gets inside the LangChain or LangGraph agent that handles high stake actions like database writes or financial transactions? Human in the loop is nothing but getting the human approval before doing any important or destructive actions. It gets human approval. If it is approved, it proceeds with the actions. If it is not approved, it replans the things. Here we have a sample LangGraph example. We have plan of action and execute action. Here we are trying to delete all the records from users table. Here we are setting up the LangGraph and here we are invoking. It runs until the approval is true. Once it approved, it prints action executed successfully. This is useful when we are deleting the records or sending emails or any important or destructive actions. Design a production multi-agent system in LangGraph where a supervisor agent dynamically routes tasks to specialized sub-agents. What are the failure modes? A supervisor node uses LLM to route the task to specialized agent. There will be critical failure modes and we can fix them. The failure modes are routing loop and tool deadlock. We can fix routing loop by having the turn count guard and the tool deadlock can be prevented using locks. This is a sample LangGraph code. Here we are defining max turns as 3. This is a supervisor agent. Here we are checking the max turns and routing the based on the task. Here we have research agent. Here we have code agent. And here based on the request, we are redirecting it to the research agent. If the question is related to code, we are redirecting it to the code agent. How do you architect long-term memory for a LangChain agent that must remember user preferences and facts across the session spanning weeks or months? Here we have two types of memories. One is short-term memory and other one is long-term memory. Short-term memory refers to the session memory. Once session got ended, like we lose entire short-term memory. But coming to long-term memory, we store this in a persistent database where we can retrieve the data even after months. Generally, this is a vector database where we are storing the user preferences, and this is session 1. Coming to session 2, here when we try to retrieve the user preferences, we get user preferences as Python or Java because we stored it in vector database and we are querying it from the stored vector database and we are printing it here. How does LangGraph's memory saver checkpointing work internally, and what happens to agent state during a mid-execution failure in a 20-step workflow? Checkpoint is useful whenever we face a crash or error. What agent does is it resumes from the previous checkpoint. If I have a 20-step workflow, if my agent got crashed at 14th step, what it does is it resumes from 13th step so that we don't lose entire flow. Here we have a LangGraph sample code. What we are doing is we are simulating crash at step 3. Here we are invoking the graph and whenever it reaches step 3, it gives runtime error and it prints the crash. Whenever we try to get the state, we get step 2 because it it is storing the previous checkpoint step 2. So when we are getting the state, the agent is at step 2. How would you implement dynamic guardrails that adapt to user role and context For example, an admin user can ask questions a guest user cannot ask inside LangChain pipeline. We can have a role-aware guardrails to identify user roles and execute our own custom logic. We can pass user context through runnable pass-through assign. So we can have the user role throughout the context, and we can verify who is asking the question and determine whether we can allow the user or not. Here we have a permission matrix. We have a policy check here. If we get role and we check permission matrix whether we can allow him or not. If it is allowed, he can perform the actions. If it is not, he cannot perform the actions. Here we are configuring the runnable pass through assign and runnable lambda policy check. If admin is asking the question, then he is permitted. If guest is asking the question, he is not permitted. In a multi-agent LangGraph system, how do you prevent one agent's runaway tool calling loop from consuming entire API budget and crashing the system? To control the budget, we can have three layers of defense. One is enforcing per agent step limit. It counts the number of steps. Once it reached maximum steps, it stops the agent. The other is configuring the token budget tracking. Once the maximum tokens are consumed, it will stop the agent flow. The other is timeout flow. After certain period of time, the agent terminates the session. Here we have configured max step, token budget and timeout seconds. Here we are configuring the lang graph and we are setting the budget to max steps and max tokens, and here we have configured the max timeout seconds. In the first step, we consumed 250 tokens. After step 4, we consumed 1000 tokens and token budget got exceeded. So we have stopped the flow.